My name is Ethan Pickett, and this is my video lab report for Soup Lab 2. The purpose of this lab is to analyze whether an object's shape has an effect on its electric field and therefore its electric force. We will compare the results of Lab 1, where we modeled two charged tapes as point particles, to our results for this lab, where we will model them as line charges. This lab builds on two previous labs by incorporating the E-field function from Lab 0 and the concept of finding the charge of a system with electric force and gravitational force in equilibrium from Lab 1. A few important ideas before we start. We need to remember that the momentum principle is an extension of Newton's second law. It states that when a system is at equilibrium, its net force is equal to zero. This is important because we will use this to assume that the electric force is equal to the gravitational force. We also need to know how to calculate the electric field for a three-dimensional object. First step is to divide the object into pieces. The second step is to find an electric field expression for each subdivided piece. The third step is to add the pieces' electric fields together, taking superposition into account. Superposition adds complementary fields and subtracts conflicting fields. This is why our electric force, our net electric force, that is, will be upwards and not to the left or to the right. The core concept behind this experiment is the difference between a point particle model and a line charge model. Here we see the electric force equation for a point particle equal to a gravitational force of 2.6 e to the negative 3 newtons. Here is the calculated charge from the last lab. A line charge model, however, uses this equation, where L is the length of the line charge, and R is the distance between the two line charges, or the distance between the observing area and the line charges. Here it is the distance between the two line charges. Calculating this out, we get a charge of 4.2310 e to the negative 8 coulombs. This is the net force diagram for the experiment. As you can see, the electric force is equal and opposite to the force of gravity. In this model, the system is the hanging tape, the surroundings are the earth and the tape below the hanging tape, and both the hanging tape and the tape below have the same charge for reasons we will get into later. Here are my input values. Q1 is my charge value from the previous lab. I used guess and check to find the charge value Q that would cause the electric force to equal the gravitational force. Here are the results for my computational model. As you can see, the charge from lab 2 is 1.7 times as large as the point particle charge. It's almost twice as large. The yellow arrow is the gravitational force, the white arrow is the electric force, and the green arrows are the electric field arrows. In this area is how it calculates out the electric fields and electric force present in the model. Here is where it calculates the electric field, and then here is where it calculates the electric force. Here are some assumptions that I made during the experiment. I assumed there was no air resistance on the tape because there was no air motion in the area where I performed the experiment, and the tapes were not moving fast for air drag to pose a potential force. I assumed that each U-tape I made had the exact same charge, and I assumed this charge is spread evenly through the length of the tape. It is safe to assume this because each tape undergoes the same charge process, and the composition of the tape is the same throughout its entirety. I also assumed that the books supporting the tape are not enacting a force while the hanging portion of the tape is levitating and they are not affecting the charges present. I also assumed that 10 subdivisions per U-tape are enough to accurately model the system. Here are my conclusions. According to my computational model, the charge is 4.23108 e to the negative 8 coulombs. This is the precise charge to set the electrical force equal to the gravitational force. This charge is a little less than twice as large as the charge computed assuming a point particle which is 2.44122 e to the negative 8 coulombs. This lab has a larger charge value because, by modeling the two charged U-tapes as a line of charges, it was able to include superposition into its equation for the electric force on the hanging portion of the tape. This necessitated an increase in the charge of the U-tapes to account for superposition. This is evident in the numerous electric field arrows as opposed to a singular electric force arrow. It is safe to assume this model more correctly models the system and surroundings because this model allows for superposition to be accounted for. This is necessary because the hanging tape has charges spread along the entirety of its length.